Let's talk about the M&M simulation I had you guys do. We were able to, in lecture 1, come up with the differential equation dm dt equals negative 0.5 mt, where m was the number of M&Ms and t was in terms of time. I now know I could solve this as a separable equation. And I'm going to assume an initial condition of about 50. I believe that's how many M&Ms are usually in a single serving bag. So now I'm going to integrate both sides, and now I'm going to do e to the both sides, and then I'm going to pull that e to the c out front as just another c, as I talked about before. And again, I'll drop the absolute value bar. Now what I'm going to do is use my initial condition to find the value of c. If you take this equation, I think you'll find that it lines up pretty nicely with what you found as an experimental value. You notice as t goes to infinity, m of t goes to 0. That is, all of mt is the transient term. And that makes sense because as we kept rolling the M&Ms, eventually, assuming that there weren't any M&Ms with m's on both sides, the value would eventually go to 0. But let's look at the second situation, where we had 10 immigrant M&Ms each generation. We would have the same differential equation, but now we add 10 M&Ms each time. So let's look at how we'd solve this. Well, first of all, this is no longer separable because of the plus 10, so now I'm going to have to use my integration factor. I've switched to prime notation, and I've moved all my m's to the left-hand side of the equation. Now I'm going to find my integration factor, and the integration factor is e to the integral px dx, or in this case, integral of pt dt. In this case, our p is equal to just the constant 0.5. So now I'm going to multiply both sides of this equation by my mu of t, and at the same time I'm transforming the left-hand side to the derivative with respect to t of my dependent variable m times that integration factor mu. Remember, this is the whole point of why we are doing the integration factor, is because the equation here is equivalent to the equation below. So when I do this, I have this, and I'm going to integrate both sides. And this is what I get when I integrate both sides. Notice I've switched from 0.5t to t over 2 because it made the integration a little bit easier for me to do in my head. Now what I want to do is divide both sides by e to the t over 2. That's the same thing as multiplying both sides by e to the negative t over 2. And now this is our solution to our M&M problem with 10 immigrants each generation. You notice the transient term here again goes to 0, and you'll notice that we actually end up with 20 M&Ms as our steady state value. So although that's not what I expected when I first ran the experiment, I think looking at students' results, you did get about 20 as opposed to 10, which you might have guessed initially. Now we had two simulations. We had one where we started at about 50, and then one that we started at 10. And the question is, does that change the equation? Well, all that's going to do is change our c value. Let's look at these two situations. Let's first say m of 0 is equal to 50. In that case, we find that c is equal to 30. And our particular solution is now this. The second term is still our transient term, and that will still go to 0 as t goes to infinity. And we look at if we start at 10 M&Ms, well then c is equal to negative 10. And that's a different particular solution. But again, you can see that the second term again goes to 0 as t goes to infinity. So the steady state solution of both of these is identical. What I'd like to do now is look at Matlab and see how Matlab would help us solve this equation as well. We're going to use a command called dsolve. One thing that you'll find out really quickly with Matlab is if you don't put the time symbol between negative 0.5 and y, you're going to get an error. And if you don't do things like, for instance, capitalize the d in dy, you're also going to get an error. Well, if you look at this solution, it says that the answer, that is y, equals c3 times exp. exp stands for e to the negative t over 2 plus 20, which is exactly what we came up with. That is for our general solution. The c3 is just a constant. Matlab will continue numbering these constants, you'll get C4, C5, etc. But just keep in mind they're any constant. What I want to do though is now I want to add the initial condition. If you hit the up arrow button on your keyboard, it'll bring up the previous commands. I'm going to add in here that y0 equals 50. So this is the case where our initial condition was 50 M&Ms. And sure enough, we get exactly the same answer that we did mathematically using that initial condition. Now let's change the initial condition to our value of 10. And sure enough, what we came up with mathematically, luckily, matches what Matlab gives us. And a reminder, this is what I typed into Matlab, and you can feel free to check a lot of your homework with Matlab. It should give you the same solutions. Lastly, I want to go to a graphing program I love called Desmos, and it's just desmos.com. And what I'm going to do is type in the two equations I came up with. What I love about Desmos is you can easily move the screen around, you can stretch it out. I'm using a tablet computer, but you can also do that pretty easily with your mouse. And you can see that these are two particular solutions from the same general equation. Remember, the general equation had that C value in it. And then we'd used two different initial conditions, and then we came up with two different particular solutions. And the initial condition where I started at 50, it's an exponentially decreasing function, whereas when I started at 10, it's an exponentially increasing function. But you notice that no matter where I start, whatever my initial value is, I still end up with the same long-term solution of 20.